welcome everybody. It's just wonderful to be here on this sunny day here in Brighton. I think actually it's even sunny in Finland now, which is wonderful. Welcome to our fifth Computing Education Research Seminar of 2025. I'm Jane Waite, I'm chairing the session today. And in our seminar series this year, we're focusing on teaching about AI and data science, and we're exploring the research that examines what children should learn about AI, machine learning and data science, as well as the most effective ways to teach about these important topics in schools. I am so excited to welcome back two speakers from our 2021 series. So they're Matti and Henrika. They presented 4 years ago on AI education. They have been doing this a long time. And so it's very exciting to see how things have changed over that time and look at some of their incredible work that they're doing now. I'm pleased to welcome our speakers, Henrika Vartiainen and Matti Tedre, as I said, from the University of Eastern Finland. Henrika is a lecturer and senior researcher at the School of Applied Education, Science and Teacher Education. Her work in AI education focuses on data agency, co-design, design-oriented pedagogy, and particularly in creative subjects like art and craft. Matti is a professor of computer science at the School of Computing. His research spans AI education, computing education, history and philosophy of computer science. I really like all the stuff on the philosophy. And he also holds honorary positions at the universities in Finland, Sweden, and South Africa. And in today's session, Henrika and Matti are going to introduce GenAI Teachable Machine, a no-code platform that helps students aged 10 to 16 to create their own AI-powered applications. And they'll share how the tool supports hands-on learning about AI and machine learning, along with the pedagogy and classroom resources developed to support teachers. And I believe they've been winning lots of awards as well for these tools. So it's award winning. So we're very much looking forward to hearing their insights. Henrika and Matti, over to you.
Thank you, Jane. So I'm Henrika from University of Eastern Finland. I'm together here with Matti, who is from computer science. And it was nice to hear that we were here last time 4 years ago. So we have been really doing a lot of collaboration together for many years now, but today we will only focus on one of our projects and one of our educational technology that we have been developing part of our Generation AI project. So could you please turn the next slide? So we have this large national project here in Finland that Matti is leading. It's about AI education. There are researchers from different disciplines and from different universities, but basically we are co-designing and developing pedagogical models and educational technologies and learning materials for integrating AI topics into school education and also in our teacher education here in Finland. And the fundamental idea here in our co-design approach is that we collaborate intensively with our local schools and with our teachers. Here's a picture from last Friday where we had meeting with our local teachers. So they have been involved in this project for 3 years now. So everything that we present here, all those tools and ideas and technologies have been co-designed with our local teachers. And also with our children, school students, we have over 200 school students working with us here in Joensuu, and also many other students and children in Oulu and here in Helsinki who are also having their own project. But we really want to focus on how to teach novice learners on how AI works. So not so much about how to use it, but what mechanisms and principles drive it. So basically we are kind of moving from AI as a tutor to AI as a design domain. And now we will tell you a few words about what we have been doing here in Finland. We know that Finland is a very unique context for doing research and development work, but like every country is. And where we work, AI education has challenges, many challenges that may not be similar to yours ones, but we have listed some of those that we have been thinking and trying to address in our own collaborative projects. So the first challenge is that we know from our own previous research and also researchers from other groups that learners have various kinds of everyday conceptions or folk theories of this kind of naive conceptions about AI. Like things like the computer, things like we do, or if I do this in social media, then that happens. And this kind of naive conceptions we know that they are also very hard to learn away, and they can also lead to sustained misconceptions. And the second challenge is that AI and data-driven AI is kind of very abstract by nature. And now there are very many new concepts and mechanisms to be learned. But then we know also that we have limited links to materials and research-based pedagogical approaches. And then we also know from the previous research that building this kind of deeper level understanding and conceptual understanding is not a very easy process. It takes time and demands effort. So mastery of AI concepts also requires this kind of sustained practices, and there is no silver bullet for that. But in our research, we have been approaching these challenges by first of all grounding our research on educational theory, for example in cognitive tradition and especially on conceptual change research, which has provided us very important insights on how we can support children and other novice learners to develop their understanding of this kind of scientific concepts and construct this kind of science-based mental models. And like I said, it's not going to be easy process, but then again, previous research on conceptual change has provided this kind of research-based insight for us on how can we design learning tasks and processes and various kinds of scaffolding structures that support learners to gradually accommodate these new concepts like training data or profiling or model inference. And then another challenge is that AI is really fuzzy for many learners and also for me coming from part of education. So another challenge is that how can we concretize this kind of very abstract concepts for novice learners? And that is a really another challenge. And then we also know that remembering or memorizing something is very different from being able to use that understanding to solve complex problems or apply knowledge in new situations. And all of these are very important skills nowadays. So then we have been also thinking that how can we also support collaborative learning and this kind of collaborative problem solving also in our AI education. And for that kind of activities, there is sociocultural theories and theories of distributed cognition that have provided us very much groundings to do that. So basic idea in our learning project and lessons is that we always ground the activities into real life context, and then we try to scaffold learners to solve these kind of meaningful problems so that they can build their understanding together with their peers. They can share their ideas, they can share their interest or expertise when they are making sense of this kind of very unfamiliar concepts along with AI's role in society and in everyday life. And then we also know that AI systems can reinforce various kinds of social hierarchies and inequalities. And then we also know from previous research that youth also often feel this kind of powerless against this kind of massive data collection and AI-driven profiling and things like that. So we also, I think, we really need to be able to develop AI education that is more than this kind of technological or social, but is also about how to make change happen. So then we have been also thinking that how we can also support learners to question and resist this kind of oppressive data practices, and how we can support them to see themselves as this kind of agents of change. People who can propose alternative solutions and take informed actions to shape a more just and sustainable AI futures, for example, through activisms or policy making or community-based projects. And for that critical pedagogy and transformative learning that grounds on the work of Paulo Freire has provided us very important insights. So the basic idea here is also, again, that the learning projects that the children design and make, in those projects, they are not only developing their conceptual understanding of AI, but using and applying that evolving understanding for exploring critical and ethical questions like how these tools may reinforce biases or oppressive power relationship structures and practices and so forth. Because I think that developing not only awareness, but understanding is highly important for this kind of transformative learning and agency.
We are from Finland, and it's a unique country like every other country is. And our challenges are, for instance, in this domain are that, we need to make our education suitable for people who can't program. So we don't have programming in school at the level that UK and US may have. I'm not sure about that, but we don't have programming in curriculum. So everything we do needs to start from these kind of, these realities. And also, I think that that it also applies to many other countries, that if something needs programming, then it's probably not going to happen in most countries of the world anyhow. So what we do is we focus on no-code approaches, we focus on collaborative learning, and we make sure that students can work with their own data. And this has been a revelation to someone like me from computer science. I kind of, didn't. I always thought that, hey, it's great to do data science projects with, with weather data and so, but when kids actually do use their own data sets, it kind of, it really starts to shine. So now we are now showing one platform. So we develop all kinds of platforms for learning. And this time we're going to show you something that was born out of frustration with Google's amazing Teachable Machine. So this is how Teachable Machine looks like, right? So when it came out, it was like, wow, this is really cool. So every computer scientist was like, oh, amazing, you can do a classifier with this. So you can make your own, data sets and training data and then train the system, and then it recognizes stuff. And computer scientists are like, wow, this is so cool. But everybody else is like, okay, so what? So what is the use? I tried to show it, and then people are like, huh? Okay, so you can do this. Oh, right. And because it doesn't, quite excite everybody, we thought that we want to make something, we want to take it from here and make it much better. Google's Teachable Machine has also some other problems. It uses GA, which means that it's not GDPR compatible, so privacy is not guaranteed, which is a must in our schools. It doesn't really offer anything for collaboration. You need to all sit on the same computer and so on. If you want to do anything with the model that you have just done, you can click the export button there, and then you can take it to a different environment, which makes things again really, really hard because things are always broken. I'm sure that if you have tried to do that, it's not very, very easy. And you need to know programming if you embed these models into something else and so forth. And it doesn't really provide you XAI that much. So we wanted to make Google's Teachable Machine much better. So we started from defining the big ideas that we wanna teach, and the big ideas that we wanted to teach with that was something like, firstly, how do data-driven and rule-driven automation differ? The kind of a fundamental question about AI education. The second is, how can I automate things using examples? Or how do I teach a computer to do something, but Jane will whip me every time she hears these anthropomorphisms? Then we want to teach basic concepts like what is data and a bunch of others. How much data do I need? What kinds of data? Then how do I improve it? And that's where I think a lot of learning happens when things don't work. A lot of learning happens there. And then what harms can these systems cause, and for whom? So I'm just going to show our Teachable Machine here because it's just it's very. I mean, the starting is exactly like Teachable Machine is. And what I'm going to do here, I borrowed from my 3-year-old. This is a wolf. This one. And this is a bunny, and this is going to be a scary, thing. So if you are, so this is a warning. If if you are scared easily, then but first I need to kind of like Google Teachable Machine. First I need to create a data set of the background. So I'm just gonna take I don't know how many do let me move here a bit. And now I've got 22 images of me. And then I want to get this bunny data set, and then this is the bunny, and then this is how bunny looks like. Bunny is here, and oops, it went out the picture. So then kids learn all those things that kids learn using Teachable Machine, like curation. Like these are not actually images of bunnies, so you need to remove them. You can drag them between the between classes, and you can include also you can do all kinds of things. Then I need to wolf. I need to add a class for wolf, and let me do 2 classes of wolves. One is a wolf that just looks around here, and but kind of watches and just basically looks scary. And then another wolf that is an angry one, so it growls. Angry. All right. And then this wolf has its mouth open like that. Right. Now let me make this an angry wolf. All right. Okay, here I have got 4 classes, and then I train a classifier. Exactly like you do with Teachable Machine. And this is where you stop with Teachable Machine. This is where you are done. So we added a CAM XAI bit that tells you which area of this image here contributes most to the classification result. So wolf angry is 90% here, and it's the wolves. It looks like the tongue. That's really, it looks like it's the tongue that causes it. Okay, that's really good for debugging, but it's not a feature in Teachable Machine. Right, it looks like it works fine. Background is now here, bunny is now here, then a wolf that is that is just a wolf, and then an angry wolf. All right, and then kids go on, and then they do their actual app. So this works so that that for each of these classification results, you can define an action. So for when there is only background, then let me show it no text there. I could record a sound, but I know that if I'm talking to you at the same time and I record this sound, then this system steals my microphone, and then odd things happen. So I need to upload a sound, and let me make a kind of a this should be a sound that it's kind of a humming of a wind, and let me share computer sound and maybe show also a picture, so let me also show here. So this output here is a kind of a preview what your mobile phone shows, when it's run on a mobile phone. So let me add here prairie. Bunnies don't live on a prairie, but this is a different bunny now. Right, okay. When this system recognizes a bunny, like that, then we don't want to show a bunny text. Kids love showing all kinds of texts, they make all kinds of really good things, but but I think that what we want to do when a bunny is shown, we want to play this sound like this bunny who doesn't think anything bad is gonna happen to him or her, and then maybe we want a bunny picture. So I could upload a bunny picture, drag from anywhere, but let me use one of these images. Oops, let me use one of these images that to make it easier. Right. So when a bunny is shown, that's I could probably show a bunny picture there, but okay. And then I need to make a wolf action, and this is how a wolf looks like. So no text. Or maybe I could add the text. Nothing scary here. Right? And then I upload a sound. kids love recording these sounds. It's the most fun when they do all their own sounds. But you know that this is the sound where the so this is the kind of a panting wolf. Nothing scary here. And let me also add maybe a wolf picture. Okay, that's a wolf. That is nothing scary here. Don't you can go and play whatever you like, little bunny. And here is the wolf angry. What happens when when the system recognizes wolf angry? There, then no message, but but let me play a angry wolf sound. Wolf growls. This is how it sounds. Oh, very scary stuff. And then let me upload a picture of wolf there also. Now this is an angry wolf. Look at that. Okay, so this is our system. Now let me try it out. So I can deploy it, for instance, to a separate tab, and it loads it for a while, and then this is how the system looks like. So whenever the classification result is me, then nothing happens there. And then when the system sees a little bunny here, then there's a bunny who just doesn't understand there's something not scary around. And then a wolf comes to picture, and when it opens its mouth, it growls. So now nothing happens, and when it opens the mouth, it growls. Okay, let me switch down the volume. Works fantastically, and this is how how easy it is to do this. And then the funniest part comes that if you have at home a bunny like that and a wolf like that, you can take that QR code and download it to your own mobile. So everybody can use their own mobile phone to use the app. And this is where kids start to test the systems. And this is where they start to understand how fragile systems are. So AI models or image recognition models are really brittle. So that if anything changes in the kind of in the initial setup, kind of a background, even lighting changes, then things just fall apart. So this is really good experience on kind of how easy they are to break. And I honestly think that breaking other students' systems is an amazing way to learn about how AI works, because you can kind of easily learn how to break them. You also get to learn. I mean, this is almost an immediate link to biases, because in every classroom there are people who make classifiers of their own faces or some of their friends in there, and it doesn't take much to find out that that if everybody in the group had blonde hair, that is the case in Finland usually, then anybody with brown hair probably doesn't work. So so kind of you take slightly different looking kid in the picture and it doesn't work anymore. A different t-shirt probably breaks the model. So so these systems are become biased super fast and super easily, and then you get very quickly into deep discussions about bias. So this can serve incredibly well for teaching about biases. So so this is the tool that we have built, and by we I mean Nick Pope, whom we stole from UK. Thank you, we're happy with him, don't take him back. This is not translated to a bunch of languages. This is kind of kind of ad hoc. If somebody comes in and says, "Hey, I want to provide a language file," then we just give the the file and tell fill it in, please. You're good to go. So the number of concepts in this is pretty big. So basically, the concepts are like training data. So basically, you do that, you do that with the first part there. Example, we call samples examples because we want to make it kind of familiar to novice learners. You learn what is a class, you learn what is a name or label if you like, you learn training process, you learn classifier, you learn what is an input, you find out what is a classification result, then importantly confidence, so that it's not 1, 0, on, off, yes, no, but it's kind of a matter of confidence level. And especially you learn that that a system can be confident about the result when it's wrong. So it's not about about being right, but a system can have very high confidence on a wrong result. So you learn all kinds of these kind of concepts that are not at all part of classical computational thinking. None of these, aside from input, are are actually concepts in classical, I mean K-12 computational thinking. You learn with an activation map, which is the XAI bit there. Then trigger, that triggers an action. Then brittleness, of course, that it works well until it doesn't. And then what does it mean to deploy a system that you build to everybody's phone in the classroom? So it's kind of we have several apps in one here. So this is a bear detector that I made using Teddy Bear, and it works on a mobile phone there. Right. What I think is super important thing for learning is this. Throughout this learning, learners maintain a direct line of sight from the final product to the tiniest bits, learning data, at the beginning of the workflow, and everything between. So they created the training data sets and they carry them out through the whole workflow all the way to the deployed product. And this gives them insight like no other approach does into higher level ideas like bias. You have a feel of data because you made it yourself, and you can intuit the bias super easily. We do have things like an API for things like confusion matrix and loss function, if you like, but we wanted to keep this really simple. So if you want to, if you have high school kids and you want to teach them those things, fine, you can do that, but they are behind an API. Yeah. So I will just very quickly show also, and then I'm done, that we wanted to go further with this, because there are a bunch of concepts that you just can't demonstrate on a virtual app that runs just on your phones. So we made this system where you can use the same thing to build robots. So that adds one thing here. The first bit here says, the robot bit tells what did you attach to the robot. So this one has one motor and one lead. And then you work exactly the same, workflow that you do with a Teachable Machine. And then you define actions. So actions now can be rotate a motor, turn a servo, blink a light, or switch on a light. And then you can build robots using almost any material. So this is how the robot looks like. This robot costs a bit less than 50 euros. So it's super cheap. So everything included, all these motors and everything costs less than 50 euros. So this is how the motor looks like. These look homemade because they are homemade at Anssi's home. Anssi is our PhD student who designed this. And then a lot of things that were built on this. So there's one cardboard robot. There's one amazing dancer robot that when it sees a certain image, it starts to dance and rotate and play music. And then all kinds of sweeper, cleaner robots using different kinds of materials, because classrooms have different kinds of materials available. So we wanted to be material agnostic or platform agnostic. And this system adds 3 more things that cannot be taught with those Teachable Machine, mobile phone things. And that is actuators. What are actuators? So, servos, motors, light, sound, buzzers, displays, whatever. Second, it teaches you about causality, because actions in here are real, full-blooded actions that take place in the physical world and not just just abstract virtual world. And then third, it teaches you about world model, kind of how the model sees the world, or sees in a way that Jane doesn't like, but so kind of a plus how the actuators cause change in the states of the world. So Uwe says that the classification is a kind of action. Yes, right, but but these are kind of physical actions. So I should talk about physical actions here. And yes, what happens on a mobile phone is also physical. Every photon that hits, my eye is a physical thing. But let's not go into the details of that discussion. It's kind of a deep. Right. But you need to have a work model because and you need to learn about accountability, because accountability doesn't happen in the world of abstractions. It happens in the real world where things fail because you modeled something wrong. You modeled maybe one of the many kinds of models of the physical world wrong. It may work. Something may work within an abstract model, but fail when taken to the world. And this also maintains the kind of a line of sight between different parts of the project. Line of sight from the behaviors of your robot to the contents of your training data. Here are pictures of the robot. So here is the kind of the power module, then the robot itself. It's not very big, and then the components. And these things that people have built with it. So Legos, cardboard. Pre-service teachers said that cardboard is the best because that's found in every single classroom. And this is a one-eyed cat that follows whatever object that you show it. That's pretty nice. I don't know why it has one eye, but who knows? These are a clock and a flower that rotates and blinks lights, and there's somebody building a robot. I'll show one more thing that I forgot. So we added something that that you can actually have the whole classroom using their own mobile phones or tablets or whatever they have to feed data to these data sets, because that makes it really interesting when 16 kids try and take pictures of for the classifier. So we have that too. All right, thank you.
Just summing up, so basically we have worked under a bunch of design principles when we have been co-designing these tools and technologies and related learning activities. So there is the no-code that Matti was telling you about, the idea of personal data and collaborative learning, and all of these ideas coming from the educational theory and research as well. And what is something that we have been also paying attention, that when we talk about AI with children, we try to do it in a way that children can relate to it to some kind of specific application. So like we talk more about like recommendation system or facial recognition or road sign classifier and things like that. And please go to the next one. And the second key principle here is that all of our co-design and development work is also based on empirical research. And especially now we have a very unique opportunity to do longitudinal research here in Finland, to follow the same children for 3 years. So we have been implementing this kind of cumulative learning paths and interventions where we teach a specific topic each time, taking like 4 to 6 hours per topic, and then build on that kind of evolving understanding when we meet the same children in the next year. This also means that we have huge amount of data from our school interventions, and we have done some analysis and published many papers about those preliminary findings and pre and post, but now we have huge amount of video data that also, so we are very keen on exploring deeper level analysis on how this kind of collaborative learning and inquiry processes emerge when we are interacting with this kind of tools, and what kind of scaffolding structures are still needed there. Yeah, and then we have some takeaways from our experiences on how to teach data-driven AI in our schools. And again, they are from Finland, but I hope there is something for you to work on elsewhere too. So there is the no-code approach, and I totally agree with Matt, because I come from teacher education, especially in Finland when the program is not a school subject. It's very important also for developing this kind of tools that the teachers have the courage and interest and agency to apply these kind of technologies also as a part of their own teaching and so forth. But like Matti was talking, I really am keen on the idea that the children can use and create their own personal data, because that's make these kind of processes not only interesting but meaningful, so they are willing to put effort when they are struggling with the systems and trying to iterate their designs and so forth. And for that kind of pedagogical practices, also collaboration, working with others and creating things with the people you with your peers and with the support of the teachers is very important for cultivating this kind of learner-centered activities. And finally, I also like to emphasize the role of this kind of hands-on inquiry, hands-on activities, where children can develop their understanding and develop this kind of conceptual understanding by making things with the help of these new tools and technologies that Matti and Nick has been developing. So by that way, this kind of very abstract, very unfamiliar concepts about AI, they become more tangible. So concepts like biases or fairness or social impact of AI, they can come, how would I say, more tangible. So in a ways that they can be explored, they can be discussed, they can be debated and so forth. So it creates this kind of process where the children are typically not only minds-on, but also hands-on when they are building their understanding of how AI works.
Brilliant. That's absolutely amazing. Can we all give Matti and Henrika like a huge round of applause? It's just absolutely wonderful.